Welcome everyone to the today's seminar. I'm Tony Roskilly. I'm a Professor of Energy Systems at Durham University, and I lead the EPSRC network plus on hydrogen fuel transportation. This webinar is part of a series that is looking at different aspects of hydrogen research in the transport sector. And this week, we are welcoming two speakers on the subject of hydrogen-compatible materials and safety, who will provide their own thoughts from a leading industrial and academic perspective. We have asked the speakers to present for around 20 minutes, and once both have finished, we will then open up for a Q&A session. So let's kick off with the first presentation. This is going to be given by Dr. Marcel Wetegrove. He's at Leibniz Institute for research on plasma research and technology. He studied physics in Rostock University, and his master's thesis was on metal hydride-based hydrogen storage materials. He continued on to do a PhD working on the characterization and synthesis of magnetic nanoparticles, and since 2020 has been a postdoc at the Leibniz Institute. He's going to give a presentation on the H2BS project on novel hydrogen barrier coatings for cost-effective and high-strength steels in hydrogen technology. So over to you, Marcel.
Yes, thank you very much for your kind introduction, and I'm delighted to have the possibility to introduce the H2BS project today. The development of reliable storage technologies harnessing the highly fluctuating energy supply from renewable energy sources is currently of the greatest importance for the worldwide energy transition, and is also identified by the German National Hydrogen Strategy as a key component in this transition, in particular using green hydrogen. Hydrogen as a transport and storage medium shows a particularly high potential for decoupling of energy sectors. So conversion of electrical energy to produce hydrogen, to generate heat in the transport sector, for transporting hydrogen in the gas grid, and also for emission-free mobility and for decarbonizing industrial processes like steel production and refineries. The corresponding infrastructure makes it necessary to expand the transport and storage of hydrogen, in particular in gas lines, tanks, valves, pressure reducers, and fittings, both in stationary and mobile applications. And as this hydrogen economy is established, a list of new markets in hydrogen infrastructure opens up. These include segments such as job coating, components for mobile and stationary hydrogen applications, the production of hydrogen tanks and pipes, adapting the gas grid to the requirements of hydrogen transport, plant engineering, production and operation of electrolyzers for hydrogen production, power-to-X plants, and hydrogen fuel stations. And concerning the use of steel in these new sectors, the main challenges are achieving resistance towards hydrogen embrittlement, reducing cost, weight, and achieving suitable operating temperatures. Steel as a construction material shows high toughness, durability, and resistance to external influences, as well as excellent recyclability. On the other hand, especially in dynamic operation, these steels are often exposed to large pressure fluctuations, up to 900 bars in the automotive sector, and these pressure changes, which are associated with corresponding mechanical loads, promote hydrogen embrittlement. Another relevant area are applications where components are exposed to lower hydrogen pressures of less than 200 bars, but here we find increased temperatures ranging from 100 to more than 400 degrees Celsius. Examples for this would be high temperature fuel cells and electrolyzers, containers that are used in the synthesis and of hydrogen from natural gas, cleaning and storage. Hydrogen embrittlement includes various effects that lead to the weakening of the material under the influence of hydrogen. And here not only the diffusion properties play a role, but also cohesive forces inside the material. The hydrogen interacts with oxide layers or metal atoms at the interface with the gaseous or liquid medium, and they make up important factors influencing hydrogen embrittlement. Also, the absorption behavior of hydrogen on the surface has great influence, and in addition to this, the diffusion of absorbed hydrogen, which can be further enhanced by factors such as stress or temperature, leading to the formation of crack networks and debris. Yes, so in the hydrogen permeation takes place via 3 steps. So this is first the surface absorption and dissociation of hydrogen molecules at the surface. Secondly, hydrogen diffuses alongside cracks, pores, grain boundaries, or directly through the crystal lattice. Third, hydrogen recombines and dissolves after crossing the barrier. And in order to hinder this permeation mechanism, a set of properties are desirable, including reduced hydrogen absorption at the surface, making surface modifications particularly interesting, a low rate of hydrogen diffusion and low solubility. This is low permeation rates in the bulk, and ideally a smooth surface with as little cracks, pores, and defects as possible. Hydrogen transport can be lowered by a few orders of magnitude by trapping of hydrogen. This is hydrogen bonding to vacancies, interfaces, grain boundaries, and dislocations. From an engineering point of view, also it is necessary to achieve excellent stability of both the barrier coating and also the steel substrate in the individual regime of the desired application. Having these basic principles in mind, the goal of our H2BS project is to enable the use of cost-efficient or high-strength steels by developing hydrogen barrier coatings, making them fit for hydrogen infrastructure. To achieve that, we are developing coating systems on a laboratory scale, and both on steel substrate and on aluminium. We measure hydrogen permeation inside a specially made cell on these laboratory samples, detect and quantify hydrogen both inside the coating and the substrate. Another vital part is the microstructural and micromechanical characterization of the coating and the surface, and finally achieving a reduction in hydrogen permeation below an acceptable level, depending on the respective application. And further down the road, we examine sensors to perform online monitoring so that hydrogen permeation can be monitored. In this project, we at INP are luckily not alone, but we can rely on the expertise of our project partners, the Herion and the MPIE. So while at INP, we are mostly concerned with the development of coating and oxidation processes to produce these barrier layers, our partners at Herion deal with the permeation measurements and stress testing of our samples, and the MPIE has very specific expertise on the microstructural and the micromechanical characterization and the characterization of effects caused by hydrogen permeation. And as a future perspective, we also want to achieve technological and economic assessment, which then opens up paths towards standardization and certification. So our team at INP is a part of the work group of Dr. Angela Kruth. And as I mentioned already we are working on the development of surface coatings. At the beginning of the project, extensive literature research was conducted to establish a baseline of state-of-the-art hydrogen barrier coatings containing various materials, including carbides, nitrides, and oxides. And we identified promising candidates. However, we found a strong variation of literature values for permeabilities, depending on the deposition methods and also on the methods used for measuring permeability. And this shows that the development and the optimization of coatings is really key to obtain high performance barrier coatings. So our further steps after the deposition of these coatings is to investigate the correlations between the microstructure and crystallinity of our barriers, and to correlate these with the barrier properties. Of course, also extensive research is needed to achieve good stability of the interface between the ceramic coating and the metal substrate during temperature and pressure cycling, and to achieve first assessment of the economic viability of these deposition processes, also with respect to upscaling potential and the potential to achieve inner coatings in complex structures. When it comes to deposition methods, we mainly use plasma-assisted physical vapor deposition methods, such as high-power impulse magnetron sputtering and plasma ion-assisted deposition. These methods have in common high bombardment with plasma at a high energy density, achieving very compact layers that are very well suited to achieve pore-free hard coatings that show good hardness and adhesion, and that avoid columnar layer growth, which could enhance fast diffusion channels. Here you can see a fast permeation measurement that we conducted on a Kapton film using our in-house permeation measurement device. It was coated with different aluminum oxide films, and as you can see, using 1 micrometer of aluminum oxide, we are able to drastically reduce permeation. Another field that we are looking into is the formation of aluminum oxide layers on aluminum substrates by using plasma electrolytic oxidation, which is a relatively straightforward method, which is environmental friendly and allows to coat relatively complex substrate geometries and avoids the need of vacuum processes. And here, thick ceramic layers can be formed by anodic oxidation and micro discharges. Also, we aim to oxidize aluminium near the surface using microwave plasma jets, which are able to reach temperatures in excess of 1000 degrees Celsius. So for the further characterization of our barrier coatings, we receive a lot of help and expertise from our project partners. In this case, the team of Dr. Klaus Taube at Herion, who is leading the characterization with respect to permeation and stress testing. And here the most interesting feature, I think, is the ability to characterize these barrier coatings with respect to relevant conditions for applications. So for pipes and valves, these are pressures of up to 900 bars and temperatures, however, below 100 degrees Celsius. Or on the other hand, looking into hydrogen storage and heat storage in metal hydrides, pressures are typically below 100 bars, but temperatures may reach as high as 450 degrees Celsius. Also, Herion conducts experiments for the exposure of samples under defined static pressure and temperature, and to achieve quantitative analysis of the permeation using a new cell test, design, and suitable sensors. So this is, I think, a quite sophisticated and large work package to construct a high pressure test cell that is suitable for pressures of up to 900 bars. So this requires approval according to technical regulations and extensive manufacturing and functionality testing efforts. And with this reference measurements on uncounted samples are first achieved to determine also the sensitivity of the setup and the sensor, and to expose coated and uncoated samples to hydrogen. Also, quantitative permeability measurements, uncoated and uncoated steel samples are possible with the new setup. Our partners at the MPIE have expertise in the microstructural and micromechanical characterization, both of the coating and the substrate, and the analysis of processes due to hydrogen permeation. These are the work groups of Professor Christina Scheu and Professor Gerhard Dehm. And here, first and foremost, a transmission electron microscopic imaging is possible of our thin layers, looking into the morphology and the crystalline composition at a nanoscale of our coatings, both as prepared and also of damages caused by hydrogen. As I mentioned, with respect to crystalline and amorphous materials, but also achieving a localized measurement of element distributions. Another important part is the micromechanical characterization, beginning with nano indentation and also the measurement of the fracture toughness of the coatings using bending beams or micropillars produced by the focused ion beam method. And also tensile testing on coated substrates is performed, while in situ monitoring the cracks that appear during tensile testing and obtaining very important and valuable insights on the crack density. Also, the MPIE has developed an electrochemical setup that allows experiments for the micromechanical testing in situ while simultaneously loading samples with hydrogen by an electrochemical method. To sum up my talk, what are the goals or the hopes and plans for our project is first, of course, to strengthen our expertise in choosing the suitable coating methods with respect to the given work pieces and use cases, to optimize the layer thickness with respect to acceptable hydrogen permeation rates. In this case, of course, thicker coatings are always desirable to achieve lower permeation rates, but on the other hand, thin films are more favorable with respect to mechanical stability, to optimize grain boundaries in pursuit of avoiding fast diffusion channels and thereby improving barrier properties. We're looking at ways to seal pores, both during the deposition process and post-deposition. And also we're investigating multi-layer systems using the complementary properties of different materials with respect to permeation and adhesion. And another important part is to look into the impact that is caused by the handling and welding of workpieces, and to come up with strategies to achieve functional systems in this context. And with that, I would like to thank you very much for listening.
Okay, thanks very much for excellent presentation, Marcel.